This is learning objective 19. We will be discussing hydrostatic pressure forces on submerged planes. So here's a figure we got from the textbook, figure 2.6. And this is to help you understand hydrostatic resultant forces. So looking at this figure, to give you an orientation, we have a plane, a plate. It's odd shaped. It kind of looks like this weird looking potato you can see in the lower part of the screen. On the side view, what we call the YZ plane, that's looking from that plate from the side, so you can see how it becomes extremely thin because it's at the side of it. And this plate is inclined in respect to the surface of this liquid. The planar view is what you would look like if you were looking straight down from the surface. Okay, so the side is, if you can imagine if you were in a lake and you stuck a plate sideways in the water, the side view is if you were looking, dropped your head below the water and looked, you would see it. The planar view is if you were lying on some kind of raft above the water and looking straight down and you saw that same plate. Okay? So we're going to find some terms here so you can better understand what we talk about when we say hydrostatic resultant force. Key to remember for this, for all the stuff we're talking about today, hydrostatic. So it's got to be static. The equations and analogies we use here are all based on the fact that the liquid is going to be static in this case. So the first one we're going to talk about is the centroid. It's the geometric center of your shape. So in this case, we put the center there. In many cases, if it's a circle, it's right in the middle of the circle. If it's an odd shape, you may have to use some calculations to find the centroid, but this is where it's determined to be. So it's a geometric center. Center of pressure is the point where, so the pressure acting on the plate is pressure is force over area. Well, if we were to sum up all of that pressure and you take the area of it, it produces what we call resultant force. So if we were to take that pressure, multiply by the entire area of this plate, we would get a resulting force. And where that force, if you were to basically take all that pressure and turn it into just one pinpoint force, that pinpoint of the force would act at the center of pressure. Alright, so the center of pressure is if all that pressure was constricted to being a force at one point, that is where that force would react. Theta up there in the corner between the free surface and the plate, that's your slant angle. So everything on this the plate is in line with, is called the slant. It's slanting downward. And so the slant angle is the angle between our free surface and your slant length. Now we get into the slant. So you see that we have the y-axis there. Everything along the y-axis is called, it uses the nomenclature of slant, and we use the y to define it. So if we want to talk about the distance along the slant to the centroid, we would have y sub c. So that's the slant distance from the centroid. So if we went from the surface and traveled in plane along with the plate, when we get to the centroid, that would be yc. That's a distance. If we wanted to get to the center of pressure, it would be y sub cp. Okay. So everything traveling along that slant has a length of y. Okay. If we look at this, this is a basic trigonometry function. We have a slant angle y. We have a length along that distance. Slant angle theta. A distance along that is our y. You can think of it as the y is our hypotenuse. So using basic trigonometry, we can say then that we have the distance from the free surface down to that point, wherever point we're looking at, is called h. That's our height. And our height is going to equal that slant distance times sine theta. So this is basic trig going back here. We're just saying that if y is our hypotenuse, then the distance, if you went straight down from the free surface to the distance you're looking at. So say we're looking for the height of the center of pressure, it would be the slant distance of the center of pressure times sine theta, and that would give you the height down. The height is, you can see by the depiction, it's perpendicular to the free surface, okay, whereas your slant is going in line with your plane of your plate. We also have the resultant force. It's already been depicted on here. Like we said, if we took the area of this potato-shaped item, multiply it by that pressure that's feeling, you would get a resultant force. Now, we use this a lot of times in calculus and stuff. We talk about discrete items. So if we were to look at one little portion of that plate, and it's called a differential of area, differential A, then it would also have a small portion of the force would act on that differential A. So that would be our differential pressure, would be that differential force divided by that differential area at that one little spot. Now I encourage you to open your textbook and go to figure 2-6 and follow along with us. We're going to keep talking about magnitude and direction. It may be easier if you have that diagram in front of you to keep referencing what we are talking about when we say center of pressure and the y's and the h distances. Okay. So the magnitude of our resultant force is the first one we're going to talk about. We'll determine the differential area. We're going to apply the differential area. So we're going to say that if force is equal to, if pressure is equal to force over area, then force is equal to pressure times the area. And in that regard, differential force is equal to pressure times differential area. Okay. The reason we can hold that pressure constant is because we say that it's hydrostatic. The water is not changing, so that pressure it feels is going to be constant. If we apply the swim-through technique to the equation above, we could say that pressure is equal to atmospheric pressure plus that distance we went down. So remember, we go in the swim-through technique, we add pressure when we go down into a liquid. So here we have atmospheric pressure plus the density of that liquid times the gravity times the height of wherever point you're looking at. Like we just said before, if the height of any point we're looking at on the plate is equal to y sine theta, we can substitute that slant distance times sine theta into this swim-through technique as well. So now what we're just going to do is substitute the equation for the swim-through technique into our differential force, the equation underneath that differential area, and then we're going to integrate. When we integrate, differential force integrated is just going to give us force. It's going to be our resultant force. And you can see then that the atmospheric pressure, because it's constant, and that area come out, so those are going to be constant. Our density times gravity times sine theta, none of that's going to change. So we're going to pull that out. So we're left with pressure, atmospheric pressure times the area plus density times gravity times sine theta times this integral of that slant distance times differential area. Now don't get too freaked out right now. I know integrals can be a little scary to some people, but we're going to get rid of this integral pretty quickly, and it's not going to be an issue. The way we get rid of it is we take into account something called the first moment of area element dA about the x-axis. So this first moment about the x-axis, you can find more information about it in Appendix A9, but I'm going to tell you what comes of using this first moment is we can say then that the integral of the area of the slant distance times the differential area is going to equal that slant distance to the center, to the centroid, times the integral of the area of the differential area. Now that integral on the right side of just the differential area is just going to be area. So that integral is going to go away when we substitute this in to the equation above, and so you get a resultant force equation that says the resultant force is equal to the atmospheric pressure plus density times gravity times the centroid slant distance times sine theta, all times the area. Again, we can substitute the h's for the y sine thetas, so we can also say that equation as resultant force is equal to atmospheric pressure plus density times gravity times the centroid height, all times the area. This is equation 2.26 in your text. When we talk about the direction of the resultant force, it's pretty easy. It's always going to be normal and perpendicular. Normal is the same kind of as perpendicular to the wetted surface. Okay? So if you think about what we're saying with that, if you were to drop into a pool of water, you would feel pressure on the front, on your back, anywhere that's normal or perpendicular to your body, that's where the pressure would be felt. Okay? So the distance is always going to be perpendicular. The direction is always going to be perpendicular to the surface. Now when we talk about location of that resultant force, like we said before, all that pressure can be interpreted as, if we treat that pressure as a one pinpoint force, we can say it all would act right through the center of pressure. So we say that the location of that resultant force is then at y sub cp, or the slant distance to the center of pressure. We also say that the center of pressure is always below the centroid. Now, there is one caveat to this, in that if the flat plate were to be completely flat on the ground, so it's a horizontal surface now, well, there is no point technically lower than where the centroid is, because the centroid is, if you moved along the plate, you're always at the same height. So in that situation, the center of pressure would be co-located with the centroid. So the only exception to this rule is if you have a horizontal plate. So that means that the plate is parallel to the free surface. Okay. If you were to have that situation, then the center of pressure would be equal to centroid. In all other cases, which we're dealing with right now, the submerged slant case, then you're going to have a center of pressure is below your centroid. So it always has to be below it. And we can see in the equation that they derive in equation 2.35 how that would make sense. Because everything you're going to get on the right-hand side is going to be positive, right? We have a positive distance down. Your density is going to be positive. Your gravity will be positive. Sine theta is going to be a positive. Your moment is going to be positive, and the resultant force is positive. So all those things are positive. Well, if we add a positive value to the centroid, then the center of pressure has to be greater. So the only case where it could be that the center of pressure, that it's not greater than the centroid, is if something on the right side equals 0. So we said the horizontal situation. If you get the horizontal situation, your slant angle, your theta, becomes 0. Sine of 0 is 0, so that whole right portion of the equation goes to 0, and then you would see that the slant distance to the center of pressure would equal the slant distance to the centroid. So for all cases we're going to deal with, you can just assume, you can stick with this for the location of your resultant force. Now that moment that we have right up there is the moment of inertia about the centroid x-axis. If you look in figure 2.7 of your text, they have some good examples of what these moment of inertias would be, how to calculate them for different shapes. I recommend you tab your text here, because we will definitely, if we ask you a question, we'll either give you the moment of inertia or we'll tell you the shape, and it will be in figure 2.7 for you guys to figure out. Okay? So definitely want to highlight figure 2.7 in your text. Finally, we're going to talk about net hydrostatic force. So when we talk about net hydrostatic force, we're saying that, so resultant hydrostatic force is the force of that fluid on a plate. But when we talk about net, we're saying, well, what if we know that the other side of the plate, it's atmospheric pressure? Well, if on the other side of the plate it's atmospheric pressure, and we know that the sum of the forces equals 0, because we're looking at a hydrostatic situation, then we would have atmospheric pressure acting on both sides, because a component of that resultant force is atmospheric pressure. Well, those atmospheric pressures would cancel out, so your net resultant force would look very much like your resultant force equations, except that we just don't have an atmospheric pressure term. Okay. So what you get is a density times gravity times the slant distance to the centroid times sine theta times the area, or density times gravity times the height of the centroid times the area. Both will give you the same answer, and these are equation 2.27. To determine the direction of the net hydrostatic force, is still going to be the same. It's always normal to the wetted surface. The location, you're going to find out by substituting that net resultant force for your resultant force in equation 2.35, and what you get is this reduced equation here of your location of your center of pressure, your slant distance to the center of pressure, is equal to the slant distance to your centroid plus that moment of inertia about the centroid divided by the slant distance to the centroid times the area. It's equation 2.36. Now on your reference data card, we do have a section that talks about hydrostatic forces. It's right here under static fluid. A key there I want you to bring your guys' attention to, it's under static fluids, which means you can only use these equations if the fluid is static. We will get into cases in this course where fluid moves, and at that point you can no longer use this equation. There's too many other variables going on. For static fluids, this is fine, but I also want to key you into that these are the equations for the resultant net hydrostatic force. So another assumption you have to make is that there is atmospheric pressure acting on both sides. If they don't tell you that there's atmospheric pressure on both sides, or you can't, it doesn't seem like a valid assumption, then you can't use these resultant equations. You have to go back and start using just the magnitude and location equations for resultant force. Only if there's atmospheric pressure acting on both sides can you use these equations for the net hydrostatic force. Also want to key you into one quick thing, going back to our diagram. So if you look in the upper left portion of the liquid where it says atmospheric pressure and then liquid, next to it there is a downward facing arrow and two lines. If you see a downward facing arrow and two lines on top of a liquid, what that's telling you is at the surface of that liquid is atmospheric pressure. So often you'll see atmospheric pressure written, or they'll tell it to you like they do in this case, but if you were to just see that downward arrow and those two lines, that is also a way to indicate to you that you have atmospheric pressure at that surface. If you have any questions about this lesson, please seek your instructor or leave us some feedback on the discussion board.